Welcome to your last video on Chapter 5. This is from textbook section 5.3, and in your notes, it's 15 through 19 on the handouts you're going to get in class. Our learning targets today, we're going to talk about the general multiplication rule, use tree diagrams to calculate probabilities, and when appropriate, use multiplication rule for independent events. We're going to play a game. In class, we'll do this live. Today, we'll just kind of simulate it. 5 cards total, 2 jokers, 3 aces. Player chooses the first card and records the results, then chooses the second card without replacement, records the results. Player wins if they get a pair of aces or a pair of jokers. So we're going to simulate first what we think the probability is, then we'll calculate it using theoretical probabilities, using what we use for tree diagrams and multiplication rules. You're going to set up your cards like this. You're going to go to random.org/playing-cards. I'm going to draw 2 cards from a 1 deck, include 3 of the 4 suits since we want 3 aces, and only check aces and check both the jokers so you can get 2 jokers. And then make sure that that's show remaining cards face down. So I've got that set up. We're going to go ahead and get started. I'm going to draw, and I'm going to keep track of it just mentally. So in this scenario, I have 1 joker, 1 ace, first joker, first card joker, second card's ace, not a winner. So I'm going to do these 10 times. All right, I got a winner, an ace and an ace. So 1 win. Not this time. That's 3 total, 1 out of 3. Hey, both jokers, that's 2 out of 4. 2 out of 5, that's not a winner. Hey, both jokers, that's 3 out of 6. Not the same. 3 out of 7, not the same. 3 out of 8, not the same. 3 out of 9, and not the same. So 3 out of 10. So in my scenario, now you're going to have different results if you do this on your own. I'm not really concerned about what the first or second card is, but in my results, I got out of 10 trials, 3 out of 10 were a winner. So in our scenario here, based on the whole class data, what's the probability of winning this game? Well, I just did this myself. So if I'm only going by what I have, then I would say 30%. Now, I don't know if that's right or not, but we're going to find out using what we call a tree diagram. So this has already kind of been started for you, but what we're going to do is we're going to fill in the boxes with the correct probabilities. Double click on the diagram to edit the boxes. Well, you can write on your own here. Let's talk about what we have first. We know we have 3 aces and 2 jokers to pull from. So our first pick is either going to be 3 aces or 2 jokers, right? So the probability of getting an ace is 3/5. Probability of getting a joker is 2/5. Now, we've already done that first draw, so let's look at the second draw. We have 1 less card, but we have 1 less ace, because if we've drawn from here, then our first card being an ace, I only have 2 aces left. So the probability of getting an ace, given that my first one was already an ace, is only 2 out of 4. Now I have both my jokers, so it's still going to be 2 out of 4 to get a joker on the second pull, because I have 4 cards total, but 2 of them are still remaining to be jokers. Does that make sense? Let's go down here. See if you can think about what's going to go in these boxes. I've drawn a joker. I still have 1 less card, but I have all my aces. So 3 out of 4 is going to be the probability of getting my second card an ace if I've drawn a joker the first time. But I have 1 less joker. So now my probability of getting a joker on the second pull is 1/4. So the last part in the tree diagram is when we're going to follow the branches and we're going to multiply. So if you look at here, you got 3/5 times 2/4. That's going to be 6/20. That's 0.3. Now let's do the same thing with the other ones. 3/5 times 2/4 for first card ace, second card joker. Again, 0.3. It's actually the same. The third one, 2/5 times 3/4. If you follow that branch, 6 out of 20. So the probability of the first card be a joker, second card is an ace, is again 0.3. And that last one, 2/5 times 1/4. Probability of first card being a joker, second card also being a joker, is 2 out of 20, which is 0.1. If you do the math on there, these should add to 1. 0.3 plus 0.3 plus 0.3 is 0.9, plus 0.1 is 1. So those are all of my individual probabilities added together It's a legit probability distribution because they do add to 1. So let's talk about the theoretical probability of winning the game. Now remember, we are a winner if we have a pair. So if our first card's an ace and our second card's an ace, that's a winner. If our first card's a joker and our second card's a joker, that's a winner. Now remember what I said from my simulation was at 30%. The theoretical probability is not just that, but it's also going to be that combined together. So 6 out of 20 plus 2 out of 20, or 0.3 plus 0.1, 0.4, 40%. So the game has a theoretical probability of winning at 40%, which is a little bit higher than my one trial. Now, if we combine our class data, hopefully we get results that are similar to it. So for this one here, what's the probability that the first card was a joker given that the person won the game? So out of all the winners, again, out of the probability of the first joker, the first card was a joker given we are a winner, well, that's going to be this 0.1, because you either go the first card be an ace or the first card be a joker. Well, we're going to follow this branch here. But out of the winners, that 40%, only 10% of them had the likelihood of having that first card be a joker. So it's that 2 out of 20 plus the combined 6 out of 20 and 2 out of 20 added together. So notice that these are kind of together, but really it's just 0.1 out of 0.4 or 1/4, 25%. Question 7, given that the second card was an ace, what is the probability that the first card was a joker? So given that the second card was an ace, what's the probability the first card is a joker? So the second card is going to be an ace where? Well, right there and right there. So those probabilities are both 0.3. Now, out of those 2.3s, one of them had the first card be a joker, and that was this following this branch here, this 0.3 highlighted in green. So it's going to be half. It's the 6 out of 20 divided by the 2 6 out of 20s added together, 0.3 out of 0.6, 50%. Now let's talk about a different scenario we can use a tree diagram for, and that's coin flipping. Here's the scenario. We want to flip a coin 3 times. You know, with a coin, those are independent events. You're either going to get heads or tails, and one flip is not dependent on a previous flip. So they're all going to have a 50-50 shot of getting a heads or a tails. So let's have 2 events. Event A, first toss is a head. Event B, second toss a head. And you can see them listed out here. Well, let's fill in that blank. If I flip it 1 time, I'm either going to get a heads or tails. Those are both going to be 50%. Now on my second flip, it doesn't matter whether I got a head or a tail. I got a 50-50 shot of getting a head or tail on that second flip. So again, those are both going to be 50%. They're not dependent on the previous one, like the card drawing activity. Same thing for the third flip. Those are all going to be 50%. So if I want to know what's the probability of getting all 3 heads, well, I'm going to multiply 0.5 times 0.5 times 0.5, which is 0.125. That's 1/8, by the way. If I do the same thing, well, like first one's a head, second one's a head, third one's a tails, it's still 0.5 times 0.5 times 0.5. In fact, they're all going to be, because if you follow the branches along there, they're each going to be 0.5 times 0.5 times 0.5. So 0.125 ends up being 1/8. And let's answer the questions. Are the events A and B independent? Well, yeah, you're flipping a coin, right? That does not impact a future flip. So yeah, knowing whether the previous flip was a head or tail does not change the probability that the second flip will be a head or tail. Coin has no memory. Each toss is independent with the probability of 50-50 being a head or tail. Now, what's the probability of getting a head 3 times? Well, we only have one scenario in this situation where we have 3 heads. So it's going to be 0.125. Intuitively, if you just kind of jot out your sample space here, these are all equally likely. There's only one of them out of 8 that have it, so 1/8 is where that comes from. What's probably getting ahead 2 times? Now we have more than one option here. So you think about where does H occur twice? Well, it's here, here, and down here. So there are three scenarios where you are getting heads twice. Now it just depends on the order where the flips happen. So exactly 2 heads is HHT, HTH, or THH. So if you add the 3.125s, you're going to get 0.375. But again, using your sample space, you know, it's really just going to be 3 out of 8, right? 3/8 is the same thing as 37.5%. So you have a couple of ways to kind of think about that. All right, part D, conditional. Given that the first toss was a tail, what's the probability of getting at least 1 head? So the first toss in this scenario has to be a tail. So I have to follow the branches down here. And I'm only concerned with these numbers. So out of those numbers, probability of getting at least 1 head, so I got 2 H's here, 1 H there, 1 H there, that occurs 3 out of those 4 times. So if you look at the math behind it, symbolically, P at least 1 head, vertical bar, means given that the first one is a tail. So 3 out of those 4.125s have 1 head or more. So 3 out of 4, 3 times 0.125 divided by 4 times 0.125. Again, looking at your sample space here, you can see, well, if I'm only concerning that the first one is a T, then 3 out of those 4 are going to have at least 1 head. All right, now let's talk about the words at least 1. People with O negative blood are universal donors. I actually have O positive, so I'm not there, but I don't know anybody that is O negative. Maybe you are. Any patient can receive a transfusion of O negative blood. Only 7.2% of the American population has O negative blood. If 10 people appear at random to give blood, what's the probability that at least 1 of them is a universal donor? What is the probability that an American has O negative blood? Well, we're given that 0.072, 7.2%. Part B, what's the probability that an American does not have O negative blood? That's the complement. Subtract from 1. Part C, if there is not at least 1 universal donor out of 10, how many universal donors are there in the sample? Well, if I don't have at least 1 out of those 10, then I would assume that I have 0. Think about it. If there's not at least 1, then there are nobody in the sample that are universal donors. So we can think about this problem like this. We can say the probability of at least 1 is 1 minus the probability that none are O negative. 1 minus the probability that none are O negative. Now, how do we do that? Well, let's start with thinking about what that means. At least 1 minus the probability that none are O negative. Now, I want you to imagine for a minute, if none of them are O negative, that means out of 10, we're talking about 10 people. Now, remember what O negative was, I forget the percent, 0.072. So none of them, the probability that an American does not have O negative blood is 0.928. But we're talking about a sample of 10, right? We're talking about 10 people. If there's at least 1 universal donor out of 10, then we have to think 0.928, 0.928, and we want to think about this happening 10 times. Now we should, I should warn you that these numbers are independent of each other, right? Like one person coming in is not affect the probability the next person come in is not going to have O negative blood. So there's an easier way to do multiplied by itself 10 times, and that's using exponents. So what we do is we say 0.928 to the 10th power. We subtract that from 1, and that'll give you 52.6%. So let's just check that in a calculator real quick. So let's recap on this case. We have 7.2%. That's the likelihood of one person, just randomly picking one person in the population having O negative blood. That means the probability that someone does not have O negative blood is 0.928%. If we raise that to the 10th power, that's the probability that nobody in a sample of 10 has O negative blood. Which means that if we subtract that from 1, that represents the probability that at least one person on a group of 10 is going to have O negative blood. So look at that calculator progression there and jot that down so you know how to do that. And there's your answer, 52.6%. So let's summarize what we talked about here. We talked about the general multiplication rule. So if I want to know what's the probability of two things happening, A and B, then I'm going to multiply their probabilities together. If they're independent, then they're going to be this, there is no given. All right. So if I want to know what's the probability of A given B, or A and B, remember that's and. If you recall that that card tree diagram we drew out, that second draw was impacted by that first draw. So you gotta account for that. But if they're independent, they're like the coin flipping. There is going to be no changing of those probabilities. But either way, we multiply those together. The at least one is always going to be 1 minus the probability that none are occurring. Tree diagrams. I'm going to label the probabilities on each branch. Compute the and probabilities at the end of each path. Multiply all the branches along that path. So we're going to times. And then we're going to get our ands at the end. And make sure those ands add to 1. Pause the video, try to check your understanding on your own. And then unpause it so we can check our answers together. Okay, question 1. A computer company makes desktop, laptop, and tablet computers at factories in 2 states, California and Texas. The California factory produces 40% of the company's computers, and the Texas factory makes the rest. Of the computers made in California, 25% are desktops, 30% are laptops, and the rest are tablets. Of those made in Texas, 10% are desktops, 20% are laptops, and the rest are tablets. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center and observe where it was made and whether it was a desktop, laptop, or tablet. For this first one, we're going to construct the tree diagram. Here's an example of what that would look like. Now, in this problem here, notice that they give you the 40% from the Texas factories. Or excuse me, 40% from California. Texas makes the rest, right? We weren't given Texas's, but if we know that the rest has to add to 100, this is going to be 1 minus 0.4. So now we know Texas's. Now we're given the first two, we're given the desktops and the laptops, and we're not given the tablets. But if you add these two together, that's going to be 55%. So that's 45% for tablets if they're from California. And then again, similarly, add the desktops and laptops 30%, 1 minus 0.3, and that's going to get you your 70% tablets for Texas. And now to get your ands, simply multiply. So 0.4 times 0.25 0.4 times 0.3, 0.4 times 0.45, 0.6 times 0.1, et cetera, et cetera. Make sure these all add to 1 so you know you're doing it right. And once you've done that, you've made your tree diagram. Now let's answer the following questions. Find the probability that the computer is a tablet. Well, let's look at our tree diagram. We have in 2 scenarios where the computer is a tablet. Whether it comes from California or Texas, we got 18% of the computers from California being tablets, 42% of the computers from Texas being tablets together. I'm going to add those together. You're going to get 60%. So 60% overall of the computers happen to be tablets, 0.18 plus 0.42. Part C. If we select 4 computers at random from the distribution center without replacement, what is the probability that at least one of the computers is a tablet? At least one. Probability of at least one is 1 minus the probability that none are tablets. So let's think about where none are tablets in this scenario. 60% are tablets, 40% are not tablets. We're selecting 4. So in the blood donor case, we raise it to the 10th power. Well, we have 4 computers selected at random. So we are going to use 4th power here. So it's 1 minus 0.4 times 0.4 times 0.4 times 0.4, or simply 1 minus 0.4 to the 4th power. That's going to give you 1 minus 0.0256, 97.44%. So the likelihood that at least one of the computers is a tablet is 97.44%. Again, here's the math behind it. Again, you have your 0.6% of the computers being tablets, so 1 minus 0.6. We're selecting 4 of them, so raise that to the 4th power. That's the probability of none of them being tablets. So subtract that from 1. That's the probability of at least one of them being a tablet. And last question. Given that a tablet computer is selected, what's the probability that it was made in California? Again, let's look at our tree diagram. We have 2 possibilities where tablets are selected, and out of that 60%, remember that this is the one from California. So it's simply going to be 18 out of 6, 0.18 out of 0.6, or 18 out of 60. And you can see that 18 is repeated down here in the denominator. That's going to be 30%, 0.3. And so the likelihood that out of all the tablets selected, it was made in California is 30%. So that concludes the lesson. I hope that's enough for you to be able to work on your 5.3 assignment. Let me know if you have any questions. Thanks for watching.